Okay, we started talking about operational amplifiers. As a matter of fact, we did cover a lot of ground. Okay, when talking about the operational amplifier, let me see if I can go back to my summary pages and see what we did. Okay, I mentioned in the beginning that an operational amplifier is essentially a differential amplifier. Okay, that's something I talked about and I mentioned in the last class. We are going to see that today. Okay, we are going to understand why we call the operational amplifier a differential amplifier. But fundamentally, it's the amplified version. Okay, the output is the amplified version of the difference between input and output. Okay, we talked about this in the last class. Okay, and owing to that, owing to the fact that there's a pretty large open loop gain, we make two assumptions. The first assumption is given from the fact that the open loop gain is really large, and then the first assumption is that the voltage that you apply on the positive input terminal and the voltage that you apply on the negative input terminal are the same. That's called the virtual short. The second assumption is the input resistance of this guy is infinity, meaning that the current going into the terminals of an op-amp is zero. Okay, so what do I mean by input impedance or input resistance? If you were to look into the resistance, if you were to look into the terminal over here and try to see what resistance you will encounter, that will be infinity. Okay, meaning that there is no current flowing through into the terminal of the op-amp. Okay, then we talked about the saturation linear regions. Okay, there's a positive saturation, negative saturation, and there is one region, okay, between the positive and negative saturation where the gain is A. Okay, rest of the places the power supplies limit the output voltage possible. Okay, that's the active region. So the slant slope region with gain, that's the active region. Okay, here is a inverting amplifier. Okay, the input is applied on the negative terminal and the feedback is always provided to the negative terminal in this class, regardless of the circuit. Um, the feedback is always provided onto the negative terminal. Okay, so given the fact that the input is applied to the negative terminal here, that leads to an inverting amplifier configuration. Okay, the inverting amplifier configuration is such that the output voltage is actually an amplified version. Okay, there is the amplification. And inverted version, don't forget the negative sign here. There is an inverted version of the input. Okay, the input is multiplied by some gain factor RF over RS and an inversion coefficient -1 to give us the inverting amplifier. Then there is the non-inverting amplifier. The input really is applied to the positive terminal. Okay, the rest of the argument is same. There is still a negative feedback coming in from the output. The input is multiplied by a gain. This time I have a positive gain, right? This is an input multiplied by positive gain from the fact that the input is applied to the positive terminal. Okay, that's what we looked at. Then we saw the difference amplifier, which is simply an enhancement of inverting amplifier. Instead of having one input connect to the negative terminal, here we have three different inputs. Okay. The key to notice here is that all of these currents add into this I total. Okay. The current coming in from this guy, the current coming in from VB source, and the current coming in from VC source. All these three branch currents add up into here, and then they are routed into that guy because there's no current flowing in here. Okay, so the result is that all of this behaves like a weighted summing amplifier. Show you what I mean. It's a weighted summing amplifier, RA. Okay, so at the core, it's the addition of three outputs, and then each of the inputs, this guy is multiplied by a weight. Similarly, VB, the input VB is multiplied by some other weight. The input VC is multiplied by some other weight. Okay, so all of these represent the gain. VA is multiplied by gain A, added to VB multiplied by gain B, plus VC multiplied by gain C. Okay, so this is a weighted summing amplifier. And it's also inverting because this guy, A gain corresponding to that is negative. Okay, notice the negative sign here. Okay, similarly, AB is negative as well, and AC is negative as well. So it is a weighted summing amplifier where the output is a weighted sum of the different inputs, and it's also an inverting amplifier. Okay, this is what we did in the last class. Questions, please. Questions so far. Okay, so let's continue from here. Okay, let's continue from here and move on to talking about, so here is the inverting amplifier that we looked at, the analysis for summing amplifier, okay, and the analysis for non-inverting amplifier. We're going to look at the last circuit here, the difference amplifier, okay, and let's follow the practice that we set for ourselves, even before completely analyzing the circuit, or even before we actually solve the solution to this circuit. Let's try to analytically understand and see what we want, what we will expect. Okay, let's try to look at what's going on with this circuit first of all. Okay, a positive, a voltage VA is applied to the negative terminal. Okay, that's VA. Okay, then there is the VB applied to the positive terminal. Okay, it seems this is a combination of both the inverting and non-inverting configurations. So here is a combination. So intuitively speaking, what we should see is the output voltage should have some kind of input component from non-inverting Okay, non-inverting is red, right? That is applied to the positive terminal here. Okay, non-inverting configuration. Let me output should have an amplified non-inverting component plus an amplified version of the inverting component. What do I mean by inverting component? I'm applying VA to the negative terminal. Okay, so I should see some fraction of VB being multiplied by some gain that is positive, and I should also see some VA. Here is VA, all right? VA should be multiplied by gain that is negative. Okay, let me color code this. Here is the negative gain component. There's a positive gain component. That is what I should expect to see on the V output. Okay, let's see if that is indeed the case. Okay, because this is simply a combination of inverting and non-inverting configurations. I'm going to look at the output and see if that is indeed the case or not. So in order to do that, let me copy this guy. I'm going to copy this. And before I begin the analysis, I just want to get an an intuitive feel for what the output will be. Okay. Let's see if that is indeed the case or not. Okay. So what I should see that VB should be multiplied by some positive gain. Sure enough, there is VB that is being multiplied by some positive gain. So that is the non-inverting configuration. Similarly, I should also expect to see some VA multiplied by a negative gain. That's VA multiplied by negative gain. Okay, so that's the idea of a um, a difference amplifier. Okay, this is called a difference amplifier because if you think about it, VB is multiplied by some positive gain and VA is multiplied by some negative gain. Okay, so more or less it's a weighted difference. Just like we had a weighted sum earlier in a summing amplifier, here we have a weighted difference. Hence the name difference amplifier. Okay, let's see if we can analyze this circuit now. Questions, please? Okay, for this guy, I'm not going to do the analysis. I will have you drive the process. Okay, let me start here. This is the difference amplifier. Okay, how do you want to analyze the circuit?
Can we just do the same thing as yesterday, going from left to right, follow that convention again?
Yes, we'll do that. So where do you want to begin? Let's follow the steps one by one. I'll write out the steps. Why don't I? That's exactly what you said is right. We'll follow the convention. We'll set up the current directions, apply KCL. The first step that I'm going to do is step one, is to find out the value of VP. Okay, the voltage at this terminal, at this node VP. Okay, Once I know VP and I look to express VP in terms of known voltages and known resistances, I want to express VP as a function of VB, RC, and RT. Okay, because all of these are known. This is the input applied voltage that I pretty much know what voltage I'm applying. This is the external resistances that I'm hooking up to the circuit. So all of these are knowns. Oops. VB, RC, and RD are known to me. So I'm going to use these values or these terms to express the value of VP. Okay, that's step number one. Express VP in terms of VB, RC, and RD. Okay, the next step would be to apply the virtual short. Okay, the argument is if I know the expression for VP, then I really know Vn as well. If I call this guy as Vn, okay, Vp is exactly the same as Vn because of the idea of virtual short. Okay, it's a virtual short. Okay, the next step then would be to apply KCL at node Vn. Okay, at that node right there. Once we apply KCL at that node right there, we will look to add the currents. Let's say this guy is the current flowing in, or current flowing through RA is I'm going to call this as IA. The current flowing out through RB is going to be IB. So using the three currents and then the current going into the OpAmp itself is I sub n. So using these three branch currents, I can write KCL at that node Vn. So once I have a value, once I have an equation in terms of VB, VA, V naught, I look to massage the expression to express V out in terms of VA, VB, and the resistances. Okay, so do you want to get started on this process? Okay, why don't you take about 5 minutes to work on this, and then we'll come back to see what you got.